Before diving into prediction modeling methods, it is important to first understand different types of data that you're likely to encounter, as it can affect certain modeling choices and analyses. This video is meant to provide a brief overview of these different data types, as the next module will dive deeper into the subject as it pertains to feature extraction, cleaning, and transformation. At the highest level, we can view data in terms of numeric and non-numeric types. And to clarify here, when describing a feature as numeric, I mean, does it make sense to represent the values of this feature on a number line? Is there some characteristic of order, sequence, or magnitude represented by each value? While some features, like the problem set name in the example, are clearly non-numeric, as it represents text and language in its raw form, it is important to also recognize that other features may appear as numbers even if it is conceptually non-numeric. An identifier, for example, may exist as a number used to distinguish one problem set or assignment or something else from another. But it wouldn't make much conceptual sense to compare these using inequalities or to apply arithmetic operations to their values. For example, in column A here, we typically wouldn't say that problem set 796926 is less than problem set 800112. The two values are just used to uniquely identify these two assignments. Prediction models are meant to find mathematic relationships between variables, so they are well suited to work with numeric values. This means that if we want to use non-numeric features in our models, we would need to convert them into a numeric type. Admittedly, dichotomizing data into just numeric and non-numeric types is a bit of an oversimplification. We can further classify types of data as nominal, ordinal, or discrete, and continuous. Some will further identify special cases of these as additional data classifications, such as ratio variables, as they may change how we use or interpret them within our models. Let's look at some examples of each of these. Starting with nominal data. Nominal data describes categorical data. This might include identifiers, textual data, or other non-ordered, non-numeric features in our dataset. When a feature has just two categories, we might describe this as binomial. The problem correctness feature here, for example, contains just two categories, correct and incorrect, and can be considered a binary or binomial feature. Categorical features that have more than two categories are sometimes considered multinomial, as with our affect label example here, where there are four possible values depicted. I will acknowledge that some binomial data could be considered to have some degree of ordering, but let's revisit this later. We can transform categorical features using methods such as one-hot encoding, or dummy coding as it's sometimes called, to create additional features that may be better suited for inclusion in a prediction model. Here, we can convert our affect label feature into a set of four binary features, for example. Our second data type, ordinal data, describes features that contain ordered values. This includes features that represent value scales, such as Likert scores, but also includes discrete numeric data, such as counts or other rankings. Binary data, particularly when it's converted into ones and zeros to represent the two values, can also be considered ordinal. Binary correctness, for example, conceptually represents ordered data, where correct is often considered as a higher score than incorrect. Similarly, however, from a prediction modeling perspective, we can also sometimes represent ordinal data as nominal, although doing so may ignore certain dependencies or trends within these features. Continuous data describes the type of numeric data that you might typically represent on a number line. This data is typically decimal valued and describes a range of non-discrete measures. As a special case of continuous data, ratios also often appear as decimal valued features. These, however, often describe percentages or fractions that have a different scale or interpretation as other continuous variables. Often, ratios are bounded between a set minimum and maximum threshold, which is why they may be considered separately from other continuous features. A percent correct feature, for example, is typically bounded between 0 and 100%, or between 0 and 1, as it's typically represented numerically for prediction models. There are a range of functions that can be applied to different data types to convert them into other types, like using a median split to convert continuous features into binary or ordinal features. We can also use binning, which converts continuous features into ordered multinomial features. Again, a lot of these are going to be reintroduced in the next module as well. So while again several of these transformation methods are going to be explored in future modules, the important thing to note here is that certain modeling approaches will depend on the type of data that you're working with. But similarly, there are various methods that we can utilize to transform our data into these different forms. The decisions that we make in terms of our data and modeling approaches will largely depend on what we want to use them for in practice.